Here we consider buoyancy arrangements for 4 systems that can be neutrally buoyant: boats, animals, balloons, and ice. So first, boats or barrels here. If we have some floating barrels, let's take this first one here, sitting in the water, a certain depth down into the water. That barrel is displacing a volume of water represented here. That water displaced would have a certain weight, and so the upward force of buoyancy that the underlying water is exerting on this barrel will be equal to the weight of that water that the barrel is displacing. So here in red is that upward force of buoyancy, and if the barrel is sitting low enough in the water, its upward force of buoyancy will balance its own weight, and it can be neutrally buoyant in equilibrium. Now, if we add a Greek onto that barrel, then that barrel will sink lower into the water. Here's the total weight on the combined barrel plus Greek. Here is the water being displaced by that barrel, now sitting lower. And if that water displaced has a weight equal to the weight of the Greek plus the barrel, then the upward force of buoyancy from the underlying water pushing up on that barrel can balance out that weight. And so our system can here be in equilibrium. And if third, we add 2 Romans onto a barrel, so we have an even greater weight, that barrel can still float if it's able to displace a volume of water whose weight is equal to that of the barrel plus the Romans. That way, the water below is pushing upwards on the barrel with this buoyancy force in such a way that the system can be in equilibrium, as long as water doesn't start spilling over the lip and adding to the weight of the barrel here. So that's how boats work. Now, about this fish here. That floating fish depicted here. The body of the fish is displacing some water. Let's let this represent the volume of water being displaced by that fish. That volume of water would have some weight, and that weight there is the same size as the upward buoyant force on that fish, represented by in red in this FBD. So our fish can be in equilibrium here if it's displacing a volume of water whose weight is equal to the fish's own weight. But fish are able to adjust their own density and adjust the buoyant force acting on them by adjusting the volume of an organ called a swim bladder. They can use their muscles to expand or contract the volume of this air-filled swim bladder in their bodies. So I've shown these 2 volumes, V1 and V2. V2, the volume of that air-filled swim bladder in the fish's guts there, and V1 will be the total volume of the flesh and bones of the fish. So if our fish is neutrally buoyant, then the mean density of that fish, given by the mass of the fish over the sum of those 2 volumes, V1 plus V2, if that density is approximately equal to the density of the surrounding water, then our fish can be in equilibrium here. That buoyant force, by the way, that upward buoyant force on the fish, would be given by our formula, where this is the density of the surrounding water, and the volume of the fish would be the sum of those 2 volumes, V1 and V2. The fish can use its muscles to expand the size of its swim bladder, increasing its own volume, causing the fish to displace a greater amount of water, causing the buoyant force on the fish to correspondingly increase. And this would make the net force on the fish greater, since its weight hasn't changed, but the buoyant force does when the fish's volume changes. That can give the fish a positive buoyancy, causing it to accelerate upwards or to rise. So here now, the new mean density of the fish is given by this expression. Fish has the same mass as before. The volume of its flesh and bones is the same, but it has increased the volume of its swim bladder, thereby decreasing its overall mean density to the point where it's less than the volume of the surrounding water. So we get a net force upwards, and the fish accelerates upwards. So most aquatic animals have some means like this to adjust their own buoyancy to rise or sink as they desire. Now then, taking to the skies, we can have here a hot air balloon or a hydrogen-filled balloon or a helium-filled balloon that is displacing an enormous volume of air. So that air being displaced by the balloon has a weight to it, and that weight will be the size of the buoyant force pushing upwards on that balloon. That is from the surrounding air below pushing up on that balloon harder than the air above pushes down on that balloon. There's our buoyant force. And if we're displacing a volume of air whose weight is equal to the weight of the balloon plus its cargo, then our balloon can be neutrally buoyant with balanced forces floating at a fixed altitude in equilibrium here, or drifting upwards or downwards at a constant velocity in equilibrium. Lastly then, if we sail out over Arctic waters and see an enormous iceberg here afloat, that iceberg can be it could be neutrally buoyant as well, this piece of ice, since it is displacing a big volume of water here. And if the volume of water displaced has a weight that is equal to the weight of the entire iceberg itself, then the upward buoyant force on the iceberg from the water below pushing up on it can balance the iceberg's own weight, and it can be in equilibrium. Let's break this scenario down to distinguish the volume of ice that is above water here, above the water line, from the volume of the ice V2 that is under the water line, V1 and V2. So for a floating iceberg, if we note that the buoyant force on it is equal to the weight of the iceberg, then we can say that the mg equals mg, and the mass of water displaced, that is the mass of this water, must be equal to the total mass of the entire iceberg. And let's cancel out the little g's there and replace the masses with densities times volumes. So the mass of water displaced is the density of water times the volume of water displaced. That would be V2, the volume of iceberg that is under the water. Then the total mass of the iceberg is the density of ice times the total volume of the iceberg, V1 plus V2. Rearranging that, we'll get V2 over V1 plus V2. That is the ratio of the volume of the iceberg that is underwater to the total volume of the iceberg. That is to say, the fraction of the iceberg's volume that is underwater here is given by the ratio of ice's density to water's density. So if ice is about 9/10 the density of water, then we get the familiar result that 90% of an iceberg is underwater, and the expression tip of the iceberg. So, are you a buoyancy genius? Last question, this one here is for you to figure out. You'll pause the video in a moment and consider this. If we have a bathtub here with a block of ice floating in it, and let it sit for a while in a warm room, when that ice block melts, will the level of water in the tub, currently marked right there, this level of water, will it go up or down or stay the same as this ice converts to water, to liquid? I'd like you to justify your answer here, not just a hunch, but can you use buoyancy principles to explain? So pause the video and consider how you would address this question. A related question would be, say if you've got a glass of ice water filled all the way up to the brim and you just let it sit out, as that ice melts, is your glass going to overflow or not? Okay, pause the video and address. Ready? The answer, of course, is that the level of the water will stay the same. The buoyant force on the ice block equals the weight of the water displaced. And therefore, as we argued with our iceberg, the mass of the ice block is therefore equal to the mass of the water displaced. So when our ice block converts to water, the volume of melted ice will exactly replace the displaced water.